So next we'll study about the derivation for the non-inverting operational amplifier. So that depends, they can give you the derivation of inverting op amp, or they can give you the derivation of non-inverting. Okay, so see, for non-inverting the diagram is also different. Again we have to connect it with the positive terminal and the negative terminal. Okay, so this is V out. We are giving supply to the positive terminal, that is V in, and we are giving supply, we are providing the resistance for the negative terminal. As in this case, RF is the feedback resistance and R1 is the resistance which is connected towards the negative terminal, and this would be grounded. Okay, remember how we have done for the inverting amplifier? What was the diagram for the inverting amplifier? I'll tell you. The diagram for the inverting amplifier is like this. Like we make a op amp, positive, negative. Okay, then a feedback resistance is connected to the positive terminal because that was inverting, non-inverting, and in this will provide R1 here, right, and will provide the V1 supply here, and this negative one is the grounded. So this is the diagram for the inverting amplifier. Clear? And this is the diagram for the non-inverting amplifier. Got it? In the non-inverting amplifier, non-inverting means supply should be connected to positive, right? Supply should be connected to positive. So we are giving the voltage, that is the input voltage, to the one end, and another terminal of voltage is grounded. Okay, now we have to connect the resistance also. We need to connect the feedback resistance, right? Feedback resistance would be connected between the output and the input terminal, right? So here also feedback resistance is indirectly connected with the output and the input terminal. Okay, so we have to connect the resistance R1 also. So in the non-inverting case, we'll connect the R1 resistance like this, and another terminal is grounded. Clear? And we have to measure the resistance over load resistance. So output would be connected to the load resistance. In this also output is connected over the load resistance. Okay, so can you you can differentiate between these two diagram, because if the diagram is correct, then only you can make the correct derivation. So in short, you have to cram this diagram. Okay, yeah, yeah, this is the diagram for the non-inverting. Okay, clear? Okay, now can I mark the current over here? Let us consider in the RF, I2 current is moving out of the node, and in R1 current is there, I1 moving out of the node, right? So as you can see, this is the RL. RL is the load resistance across the terminal. Okay, tell me, any doubt up to here? So this is RF, this is R1. So we can consider over here, this is Vn, this is the voltage, right? Can we consider the voltage over here is Vx? If this is the voltage Vx, then as you can see, if there is a plane wire, so this voltage should also be Vx. Vx I denoted by any term, like you can denote it by V2, V3, V4, V5, Vx, Vy, Vz. Okay, so I just noted that Vx is the voltage for the input terminal of the Vx is connected to the negative terminal. Okay, so Vx is like this. Clear? So if you know about the voltage division rule, remember voltage division rule, that is VDR. What is the formula for the voltage division rule? Okay, I'll tell you how we'll apply that. You have studied in the BT. Okay, see what is the exact formula for the voltage division rule. Suppose this is R1, this is R2, this is V. Okay, if we want to calculate VR2, then we can directly calculate the value. For that we have to apply voltage division rule, that is total voltage. Total voltage is V over here multiplied by the resistance in which we need to calculate voltage, that is R2, divided by the sum of resistor which are connected in series, that is R1 plus R2, right? So this is we are applying voltage division rule. Now we are having the same circuit like this. R1 is there, okay, sorry, RF is there and R1 is there, right? RF is there, R1 is there. So as you can see that current RF and R1 is in series, so there is a voltage across Vx. Vx means we need to calculate the voltage across R1. So we need to calculate the voltage across R1, that is Vx. How much is the total voltage? Total voltage is V out. V out is the here, okay, multiplied in which branch we have to calculate resistance voltage, tell me. In R1 only, in which resistance we need to calculate voltage? In which resistance we need to calculate voltage? We have to calculate voltage for R1. That is R1 divided by the sum of resistor R1 plus RF. Okay, got it? That will be Vx. Okay, so can I write down the formula for Vx over here? Vx we got it as R1 divided by R1 plus RF multiplied by V out. Okay, clear? Any doubt up to here? Hmm. Okay, so we know this value of Vx. Vx is equal to, can we say that Vx is equal to this Vx? Hmm. See, there is a voltage over here. As you know, there is a plain wire. So voltage across this point and this point would be same or different? Same. So can we say that here the voltage is Vx, and due to the virtual ground concept, if there is a voltage Vx over here, then there is a voltage of Vx over here also. Because there in op-amp there is a concept of virtual ground. In the virtual ground, what they said, the voltage across at the positive terminal would be the equal to the voltage across the negative terminal. Okay, if I'll give 2 volt supply here, then voltage would be 2 volt over here. Clear? So if there is a Vx over here, then at this point also Vx is there. So if Vx is there over here, so can we write on V in and Vx? Again there is a plain wire, there is a no resistance over here, so Vx and Vn would be equal to same or not? Because there is a plain wire. Okay, so can we say that V in is equal to R1 divided by R1 plus RF multiplied by V out. Just I put the value of Vx into V in. Actually that was concept of virtual ground. There is a positive terminal, there is a negative terminal. We generally assume that there is no current flowing inside it. Okay, so there is no current flowing inside it. So so we consider at this point and this point, if there is no current flowing over there, so at this point Vx, this point Vx, or we can say this one is V positive because it is entering to positive terminal, and this point it is V negative. V positive and V negative are same. That is due to the concept of virtual ground. Clear?